Hi, welcome to online tutorial series on digital signal processing using MATLAB and Python. This is lesson 2 in the series. In this lesson, we will learn about sinusoidal and exponential sequences, and we will also learn about a very important concept of digital signal frequency. If a signal is periodic, so what is frequency, and when a signal is converted from time domain signal to digital domain, how frequency changes into it. Okay, so let's start. So we start with our editor. Okay, so first of all, this is the lesson name. First of all, we will talk about a sinusoidal sequence. So sinusoidal sequence can be represented as let's say x of n is equals to a times cos, so it is a like cosine signal, into omega naught n plus phi. So these terms are very familiar to us, like a is the amplitude and omega naught is the angular frequency, or we can say digital frequency, angular frequency, or generally we say it is as a digital frequency, and where this phi is the phase. As simple as this, right? And suppose if omega naught is of some frequency, so this omega naught is, let's say, it's a periodic sequence, so this will be has some samples like this as that of the normal cosine wave, and we will learn how these samples are related to the periodicity of the sequence. So another sequence we generally have, that is the exponential sequence. So exponential sequences. So the sinusoidal sequences can be said as the subset of the complex exponentials. So let's have a simple example of this exponential sequence. Let's say x of n is equals to a into small a to the power n, right? Where n is going from minus infinity to infinity. So this a could be, there could be several cases, right? If a is any real number like 0.2, so this x of n will become like a into 0.2 to the power n. So if this number is less than 1, so this sequence will be decaying power, decaying sequence, right? And we will learn in the next videos, like in MATLAB and Python, we will try to make a program. So this a could be any complex number. Let's say if a is equals to e to the power sigma naught plus j omega naught. In that case, our xn will reduce to xn will reduce to a into e to the power. It will be e to the power sigma naught plus j omega naught into n. And obviously this can be written as, like, both these two terms are the real, e to the power sigma naught n into e to the power j omega naught n. So this could be x of n, right? So similarly we can further expand this, like x of n is equals to a into e to the power sigma naught n. So this sigma naught is a real value, and this n is obviously a number varying from minus infinity to infinity, and this particular complex number can be expanded as like cos omega naught n plus j sine omega naught n. So this is a very basic sequence, or we can say the general sequence, general sinusoidal sequence, uh, or the mathematical expression of a general sinusoidal sequences. So we talk about the real part. So this x of n has two parts, and this the complex real part and the complex component. So if we plot the real part of this xn, so this is a cosinusoidal sequence. So let's say a into e to the power sigma naught n, and it will become cos omega naught n, right? And if we say, let's have an assumption like if sigma naught is equals to 0, that means it has only e to the power j omega naught n term, then this x real part can be represented as x real part of n will be simply a cos wave, right? Similarly, we can plot it like the imaginary part of the same sequence, that will be a again e to the power sigma naught n into sine omega naught n, right? So again, if we assume like sigma naught is equals to 0, then this x of imaginary part can be represented as simply the in a form of a cos wave, a into, or in a form of a sine wave, right? So these are the very basic things. Now there is a very special case about, we will be dealing with sinusoidal sequences mainly, because they comes up with the frequency, sinusoidal sequences. So for sinusoidal sequences there is a term, or there is a special property. If I say like x of n is equals to sine omega naught n plus phi, right? So these sinusoidal sequences are periodic in nature, generally periodic. So periodic means this x of n will be equals to sine omega naught n plus capital N times plus phi. So we can write it like, so if this condition is happening, is equals to sine omega naught n plus phi plus omega naught n, then the signal will be periodic. That means after a certain number of samples of capital N, the sequence is repeating itself. So let's understand with the help of a plot. So this is our sine wave, and these are the numbers, or these are the total sequence length of capital N, after which it is repeating itself, right? So this sequence is a periodic in nature. Now there is a condition for that. Obviously this sine wave will repeat itself. This condition will hold true only and only if this particular number is a multiple of 2 pi r, or is a multiple of 2 pi, right? So in general we can say if omega naught n is a multiple of 2 pi, then, or for a like it could be 4 pi, it could be 6 pi. So this condition should hold. Omega naught n should have this kind of expression. Only then we can say that a sequence is a periodic in nature. And this particular n, like the smallest n, for which sequence repeat, for which condition is satisfied, or for which sequence is repeating, is known as the fundamental period. known as the fundamental period of sequence. So for having a fundamental period, this particular condition should be satisfied, right? So there could be this particular condition can also be written as, like we just came to the conclusion, like omega naught n should be equals to 2 pi r. So we can have it right like this: 2 pi by omega naught equals to n divided by r, right? So if this particular number is a rational number, if this is a rational number, that means a non-integer rational number, only then this condition will be satisfied. Rational number, only then sequence will be a periodic sequence. If this is an irrational number, then sequence will not be a periodic sequence. For example, if we write like cos root 3n plus 5, right? So in this case, root 3 is not a rational number, so this sequence is not periodic. Right, so this periodic or non-periodic sequence holds a very special meaning in digital signals or normal signals. So this should be, as a condition should be satisfied, like 2 pi by omega naught should be a rational number. Okay, so let's move forward and let's continue our discussion with this special number, that is the angular frequency. So let's have a little discussion about it. So this we said this omega naught was the angular frequency or digital frequency. So there are several dimensions, or we can say what is the dimension of this omega naught. So omega naught dimension will be, or we can say dimension of omega naught will be radians per sample. Remember, it is not omega radians per second, so it will be radians per sample if dimension of n is samples, right? So it's very straightforward. So dimension of omega naught will be samples per second. Now coming from the sampling frequency, if we have defined a sequence, a periodic sequence in time domain, and we are converting into a digital domain through the sampling process, so let's learn how to this omega naught dimension changes over time. So let's say a small discussion about this sampling process. Already we have discussed about sampling process in a previous chapter, but here we will be dealing specifically with respect to the frequency only. Okay, so any signal is converted to a digital signal by a sampling process, in which what we do instead, like suppose this is a continuous time signal, so instead of having at all the time indexes, we take certain samples out of it, right? This was the t index, so instead of this t, we take only some samples of it, let's say for 1 second, 2 second, 3 second, 4 second, 5 seconds. So this sampling period is 1 second in this case, if we are measuring it in the terms of the second. So we represent this number when we talk about in we are taking at nth index, so we represent t by this nt, and where t is the this t is known as the sampling time, right? And generally this time is opposite to the frequency, so it can also be represented as like n by fs. So this particular terms fs is known as the sampling frequency. Sampling frequency. Now this fs is also related to the omega. So For time domain signal we are taking as omega s, so it is equals to 2 pi fs. So this can also be written as 2 pi n by omega s, where this omega is the angular frequency and its dimension is radian per second, right? Or this also known as the continuous time frequency, right? So let's say if I have a signal in time domain like x of t, if we have a signal in time domain x of t as a cos 2 pi f naught t plus phi, or we can write it like a cos omega naught t plus phi. So omega naught is some specific frequency of this signal, and the corresponding digital signal or digital signal, a corresponding digital signal or a discrete signal can be represented as like x of n. So we replace this t by nt, and generally we assume t equals to 1 and we simply represent it by n. So let's say right now we are taking as nt and xn both are the same things. So a cos, we will have this 2 pi f naught instead of t, is this will become nt plus phi, right? Or in this case it can also be written as a cos omega naught nt plus phi. Now this complete this omega naught nt we have just taken here as this t can be written as 2 pi by fs, right? So if you look at carefully, this t can be as can be represented as t. So instead of t we can write it like this expression further as a cos 2 pi omega naught by omega s into n plus phi, and at just the starting we represented our signal as omega naught n as a sinusoidal signal, right? Like this we represent our omega sinusoidal signal as omega n. So now we can write like this signal as a cos omega naught n plus phi. So this omega naught, which we said as this was the digital frequency and this was the time domain frequency. So this digital frequency is related to like 2 pi omega naught by omega s, or it can be written like 2 pi f naught by fs, or we can write it like simple omega naught t. So generally there is one more terms is also used for this omega naught as a normalized frequency. This omega naught also named as normalized frequency. So there is a one special property of this omega naught. If you look at carefully, this omega naught by omega s will be a number, and but this number will be less than 2 pi always, because this will be a fractional number, because from the sampling theorem, if we write it like from sampling theorem, we understand this omega s should be greater than or equals to 2 times of omega naught, or we can say like this fs sampling frequency should be greater than twice of the massive signal frequency. So this f naught by fs, right, this will always be less than 1, or we can say this will always be less than 1 obviously. So this omega naught can go from 0 to at max 2 pi. Okay, or we can say in digital domain this generally this 2 pi will not hold with respect to this sampling condition. This can be written as like it will always be in this range from minus pi to pi. So the only reason to tell this is like if we talk about in terms of the spectrum, so spectrum of the signal will be from minus pi to pi, where this pi represents exactly the sampling frequency or half of the sampling frequency. So this pi we relate into the time domain signal, so this will be simply exactly fs by 2. So if we put fs equals to twice of f naught, so twice of f naught, it will be exactly pi. Okay, so these are some of the special things about this digital frequency, and we will be dealing with this digital frequency more when we'll be learning about the Fourier spectrum or digital Fourier spectrum. Okay, so in our next video we will try to generate the sequence using MATLAB and Python. We will generate this sinusoidal sequence using MATLAB and Python, and in order to refer a full scale description of this particular video, you can refer to discrete signal processing by Sanjit K. Mitra, a computer based approach, or any other DSP book. Okay, so I hope you now you will have some conceptual concept or about what is digital frequency and how frequency is related to in digital domain and how the signal is converted into a digital one. Okay, so with this we'll end this video, and in next video as a sub part of it we will write the programs in MATLAB Python for generating the sinusoidal signals. So that's it for this video. Thank you.